Hi, good evening.
Hi.
Okay, so in today's class, we are going to see the differentiation concept. Okay, we need to understand what is differentiation or differentiability. Differentiability is when we are able to find the slope of a function at a given point. So it's basically nothing but we are finding the slope of a function. Suppose if we have been given the graph of the function, okay, so we are actually finding whether the slope exists at this point. So the slope is basically nothing but a tangent to the graph. So it's nothing but we are finding the tangent. Okay, whether we can find the slope of the tangent, slope of function at a given point. In other words, a function is differentiable in the slope of the tangent. The slope of the tangent line, okay, this is the slope of the tangent line, is equal to the limit of the function at a given point. So the limit has to exist. Okay, it cannot, so that means the function has to be continuous. If the limit has to exist, the function has to be continuous, which implies for a function to be differentiable, it has to be continuous. Okay, so what this really means is that in order for a function to be differentiable, it must be continuous and its derivative must be continuous as well. We're going to see the mathematical definition of these two, of the definitions of this one. Differentiability is the smoothness condition of the graph. Yeah, it talks about the smoothness like this, okay, or maybe like this, or cannot be like this. If it is something like this one, this is not smoothness here. Here everywhere it is smoothness. Okay, everywhere the slope is, we have the slope, and the curve itself is smoothness. Okay, so it's actually talks about the smoothness condition of the graph. Here, this if you try to find the differentiability, or if the question is about to check the differentiability at this point, it is not differentiable because we are having a sharp turn. Sharp turn means it is not smooth. Let's see this. Let's continue. Okay, this will give you a clear picture of which type of graphs are differentiable and which type of graphs are not differentiable. We'll discuss the three instances when a function is not differentiable. So these are the three instances where a function is not differentiable. As I said before, we have a sharp turn here. Okay, so why do we have to say that it is not differentiable? Let's suppose I draw a tangent over here, right? And I draw a tangent over here. Okay, for this point, we are actually concerned about the point A. So for point A, the tangent will be like this, and that is if I try to draw from this line. Okay, considering this line, I can draw a tangent. And considering this graph, because it has to be continuous and the derivative should be the same. If you try to, in fact, any function is differentiable if LHT equal to RHD. Okay, this means it has to be differentiable at both sides. That is from left hand side as well as from the right hand side. I'll give the definition for this one later on. Okay, this one is left hand derivative and this one is right hand derivative. So only if these two are equal, we can say that the function is differentiable. Function is differentiable. That is left hand derivative is equal to right hand derivative. We're going to see more of this mathematically the coming slides. We will discover the three instances where a function is not differentiable. So coming back to this one, you can clearly see that the tangent, okay, this looks this one. If you have to draw this, this is how the tangent looks like. And for this curve and where I mean at the point A, the tangent is going to be look like this. Do you think that the slopes of these two tangents are equal? No, right? They don't.
No.
They don't, because this one is going in this direction and this one is going in this direction, and the slope is actually nothing but the steepness. Okay, how much it is inclined with the x-axis. So yeah, this is going in a different directions, and obviously these two tangents. I mean, the slopes of these two tangents are not equal. which implies it is not differentiable at this particular point called A. Okay, so it is, so you could remember that whenever you have sharp turns like this or like this or like this, and if you have to try to analyze the differentiability at these points, particularly this point, not about the other points.
I can't see that. I think it's a little too zoomed in.
Oh, you're not able to see?
I can only see like a zoomed in part. I'm not able to see where you're pointing.
One second. Now?
Yeah, I can see it.
Okay. Is it now only or from the beginning onwards?
Now I can see everything you've written. Before it was just zoomed in.
Okay. Yeah, just let me know whenever you have that difficulty. But
Sure.
from the beginning, whatever I have explained you, did you have difficulty or you want me to repeat what I said?
You mentioned something about the different points. I didn't get that part.
Okay, let's go back to this one. How about this first one? Did you understand?
Yeah,
Did you saw these things?
yeah.
Okay. Okay. So let's continue. So this one, yeah. Okay, so the reason for this one is it is the slope of the tangents are not equal, and for this graph it is definitely not continuous. Okay, so we have a jump over here from here to here, right? If we start from x this direction, it is a jump discontinuity, so it is definitely not continuous, which means discontinuous, and hence it is not differentiable. Yeah. Yes. So discontinuity means jump, point, or infinite. Any different types of discontinuity is not differentiable. And this one is also having horizontal vertical tangent. Vertical tangent is actually undefined. If you have a tangent like this, the slope of this tangent, as we know from the earlier classes, that is, you might have studied from your algebra 1 or algebra 2 classes, slope of vertical line is undefined, right? Slope of vertical line, I will put like this, is undefined. So that therefore, since the slope of the vertical line is undefined, hence the differentiability. We cannot say that it is differentiable at this point E. Okay. So if you have to remember, you have to remember these three types of graphs, like this, discontinuous like this, and vertical tangent like this. Okay. If you try to draw a tangent like this at this point, particularly this point, it is having a vertical tangent. Okay, so these are some of the three instances where the function is not differentiable. So you may have to remember these things. You have any questions so far?
No, I got it.
Okay, good. Let's move on. Okay, so this is what I said is mathematical definition of differentiability. It's more or less similar to the limits kind of definitions. So it's going to be pretty good. Okay, differentiability at point x equal to c. A function f is differentiable at x equal to c if and only, as I said before, this is the LHD, left hand derivative, and this is the RHD. Okay, so fx minus fc divided by x minus c. We know this, right? Let's try to understand the slope of the tangent line. Okay, let's take this graph. Okay, we'll revisit the definition later on. Let's take this graph. This is the graph of y equal to f of x, and this is the point C. You could see the graph clearly. Any difficulties, or you want me to zoom in?
I got it. I can see it.
Yes. Okay. I just zoomed in a little bit. Okay. So this is C comma f of c. This point is C comma f of c, and so I take another point x comma f of x. Okay. So now I wanted to find out the slope of this one at this point called C. So how do I do that? Suppose if we have been given 2 points, C comma f of c. Okay, I'll use this. I want to differentiate, I will use another class. This is C comma f of c. Okay, and another point is x comma f of x. So this you could consider as x1, y1, and this you could consider as x2, y2, and therefore the slope formula is m equal to y2 minus y1, y2 minus y1 over x2 minus x1. So this is going to get us fx minus fc, okay, all over x minus c. Okay, so this is basically nothing but the slope, and if I want to find out the equation at this point called c comma f of c, how do I arrive at this equation? So I can use the point slope form, point slope form. Okay, that is y minus y1 equals m times x minus x1. So here x1 y1 is c comma f of c. Here x1 y1 is c comma f of c. So I'm going to replace x1 y1 is c comma c comma fc. Okay, I'm just replacing it in this one. x1 y1 y minus fc equals, our slope is fx minus fc. Okay, fx minus fc, okay, all over x minus c times x minus c, x minus x1, x minus c. Oh no, we don't need this. Okay, that's my wrong. Actually, this is not required. This, we don't need to find the equation of the of this one. It's nothing but we just have to find the equation slope of the tangent. So this is the slope of the tangent. So here I'm actually trying to find the equation of the tangent. Equation of the tangent is not required. So this one, fx minus fc, right? This is basically nothing but the slope of this tangent line, and then you have to limit this. You have to limit such that this x approaches c. You have to say that x approaches c as closer as this point is. Okay, this x approaches c, we will be able to find out the slope of this tangent line. So here for this one we have to take the limit. So basically the differentiability m, you could say that m equal to limit of fx minus fc, fx minus fc all over x minus c, and x approaches c. If it is left, I have to put negative. If it is right, I have to put positive. This is left hand derivative, and this one is right hand derivative. Okay, and both should coincide to certain value called L. Both should coincide should to the same value. Only then we say that the function is differentiable. Okay, see, I'll just zoom out. Things are going okay. So make sure that you remember this formula. There is another version of the similar formula for the derivative. I'll give that later on. So for now, you could remember this one. This is differentiability at any point called c. Limit x approaches c, fx minus fc divided by x minus c. There is another version of the differentiable formula. We'll see that a little bit later on. Okay. Any questions in this one?
I got it.
Okay. The derivative from the left must equal to the derivative from the right. So left hand derivative should be equal to right hand derivative. Okay, let's move on. Differentiability implies continuity. Yeah, this is a appropriate statement. As we have seen, differentiability is equivalent to continuity. When we say that this is actually the result of a concept, when we say any function is differentiable, if we say any function is differentiable, which implies or the result of this is it is obviously continuous. Okay, It implies, or you can say the result of differentiability is continuity. So we have the statement differentiability implies continuity. Okay, we will see the reverse of it, which is actually not the true. We have a proof for this one. I'll just go a little quick on this one. This is not that much required. If f is differentiable at x equal to c, then f is continuous at x equal to c. We have a literal proof of this one. So what we do is we take a function which is continuous at x equal to c, showing that if x approaches fc as x approaches c. We take this one. Okay, limit fx minus fc x approaches c. Okay, so this can be written as, okay, whatever we have on the left hand side, fx minus fc x approaches c. I just multiply both the numerator and divided by x minus c. So here it is being multiplied. This part is multiplied both in the numerator and denominator. Okay, and the next step, this step, the product limit. This is a product. So we apply the product property for the limit. Then we split this into two limits like this. Limit x approaches c x minus c, and this one is another limit. So this is actually nothing but differentiability. Okay, the differentiability of the function at the point called c, so which is indicated as f prime of c. Okay, just now we understood this one, fx minus fc over x minus c x approaches c. This is basically nothing but differentiability formula. So that is why we put f prime of c the next step. And this one, if x approaches c, you can plug in here. X approaches c minus c is 0, so therefore this is going to get us 0. So this part finally we are able to get limit of, we are getting limit fx minus fc x approaches c. This is going to get us 0. So which means I can split this into two limits. Limit fx x approaches c negative, limit fc x approaches c. This is equal to 0. So if I either transfer it to the other side, or if I add this part on both sides, I can see that these two are equal. That is, okay, I can write down like this. Okay, this is equal to limit fx x approaches c is equal to limit fc x approaches c. So what can you see from this one? So this is the definition of which concept? Can you identify this?
Hmm?
Yes. So this is basically the formula of one of the concept. Which concept it is?
Like, just that differentiability means continuity, or?
No, not like that. Yeah. So this looks like a formula, or if we see that this limit of f of x x approaches c equal to this one, limit of f of c. Okay, I can write down this as the next step. This is independent of x, so I can simply put this as f of c. Instead of this, I can write down this as fc. Okay, now can you tell? So this is a formula for which concept? It's basically nothing but continuity,
Okay.
right?
Yeah.
This is what you use for continuous, right? Limit
Yeah.
f of x x approaches c, if it is exactly equal to f of c.
Okay. Yeah.
Okay, so then we say that the function is continuous. So that is why when we started off saying that the function is differentiable, and which actually gave us the result that the function is continuous. So which means any function that is differentiable, at any point, it is obviously continuous. Or else you could also check, if you have to do the problems, you have to first check the function is continuous. For differentiability, the must condition is it has to be continuous. And the left hand derivative is equal to RHD. It should be continuous, and the left hand derivative should be equivalent to the right hand derivative. Okay, these are all must conditions. And also, if it is differentiable, then it is definitely continuous. Okay, but if the function is continuous, we cannot say that it is definitely differentiable. It may or may not be differentiable. That is the converse of this statement. The converse of the statement is not always true. It may or may not be true. Sometimes it may, but sometimes it may not. Okay, let's move on. Okay, the relationship between continuity and differentiability is summarized below. If a function is differentiable at x equal to c, then it's continuous at x equal to c. Yeah, we know this. So differentiability implies continuity. Yes. It's possible for a function to be continuous at x equal to c and not be differentiable at x equal to c. So continuity does not imply differentiability. Yeah, as I said before, both are true. Okay. So these are two important statements. A function can be continuous and not be differentiable at x equal to c. So continuity does not. Okay, as I said before, continuity does not imply differentiability, but differentiability implies continuity. It's just summary points of what we have understood. Okay, let's move on. Okay, let's understand this differentiability with the example. Let's take this function mod x, or you see this is absolute value function fx. Okay, the parent function for this one is mod x, right? This is the absolute value function. This is the parent function. So this is actually transformed. Yeah, you could say translated. Okay, it is shifted to the right by 2 units. So it is shifted to the right by 2. This parent function is shifted to the right by 2 units. So we have this function fx equal to absolute value x minus 2. Okay, so it is, you can see from this diagram, it is continuous everywhere, and if you are a little bit concerned if it is continuous at 2, it is continuous. It's still continuous because I can see the left hand limit, I can see the right hand limit, and both coincides to the same value of 0. In fact, f of 2. Okay, this is also 0. You can plug it here. F of 2. 2 minus 2. So what is f of 2? It is 2 minus 2 absolute value. This is also going to be 0. And if you take the limit separately, left hand limit and right hand limit, they will also come 0. So therefore it is continuous at 2. Now what about differentiability? Let's check that. The one-sided limit, however, so we have to find out the left hand limit and right hand limit. So we can apply the formula. The basic formula for the differentiability is fx minus fc all over x minus c, x approaches c. So here we are concerned about the point 2 at x equal to 2. So the left hand derivative LHD, this is equal to limit fx minus f2, c is 2, divided by x minus 2, x approaches 2 from the left, 2 minus. Now I'm going to plug in my function, original function. So this is going to be limit x approaches 2 minus fx. You know that it is absolute value of x minus 2. So I can plug in here x minus 2 absolute value minus f2. Okay, so we can see that f2 is 0. So we take that 2 equal to 0 divided by x minus 2. Okay, so this one is x minus 2, absolute value of x minus 2. This is basically nothing but limit of x approaches 2 minus, this is actually x minus 2 only, all over x minus 2. So this is going to give us 1. Okay, oh, it's going to give us negative 1. Okay, let's see from this one. Okay, if it is x approaches less than 2, if you do like this, x approaches 2 minus, so less than 2 value. Okay, let's take some value little bit less than 2. So suppose if I take like 1.999 something like, or for let's take 1.9. Imagine that you are plugging it into here. So 1.9 minus of 2, okay, absolute value divided by 1.9 minus 2. So this is going to be 0.1 divided by minus 0.1. So we get minus 1. Okay.
Yeah.
This is going to be minus 1 because this is positive. Whatever the absolute value that you take, this is definitely going to be positive, and this one 1.9 minus 2 is going to be, it's not going to be definitely 0, minus 0.1 some value, whatever the value that you get, you're going to get this one. So it's going to be minus 1. Now let's do for right hand derivative, RHD, do in a different color. RHD, this is equal to limit. Okay, so the same formula, I'll just plug it here. This is x minus 2 minus of fx, that is 0 again, divided by x minus 2, but this time it is x approaches 2 plus, that is from the right hand side, little bit greater than 2. So you can take some random values like 2.1. If you take 2.1 and plug it here, this is going to be 0.1 and this is also going to be 0.1, which gives you positive 1. So these two values don't coincide. Left hand derivative 1 minus 1, they don't coincide. So we can say that it is not differentiable. Okay, not differentiable. Not differentiable at x equal to 2. Okay, so this is how we have to test whether our given function is differentiable or not differential, if you have to go according to the mathematical definitions. Okay, but if you have to quickly answer graphically, you could okay, you could make use of these graphs, these three graphs, as we have already learned: sharp turns, discontinuous, and vertical tangent. If it is a short short question, yes. Okay, smallest. Okay, do you have any questions in this?
I think I got it.
Okay. Okay, this one again, some example for if a graph with a vertical tangent line. Okay, so we have a proof for this one. Let's go through this one. So if you look at this graph of this one, this looks like a vertical tangent. Let's say if we are trying to find out the differentiability at the point x equal to 0, this point. So you can clearly see that, you can visually see that we have a vertical tangent here. So you can immediately say it is not differentiable. However, if we have to go according to the mathematical definition, let's find out the limit. I mean we use the differentiable formula, fx minus f0 divided by x minus 0. Fx is x power 1 by 3, so x power 1 by 3 minus 1 minus 0 divided by x. So I can cancel this. First I simplify this, x power 1 by 3 divided by x, this is equal to, this is x power 1. So if I have to cancel this part with this part, this will be 1 by x power 1 minus 1 by 3, which is equal to 2 by 3. Okay, so it is 1 over x power 2 by 3, and then you plug in x equal to 0. 0, this is denominator is 0, so therefore it is, finally we are getting undefined. So that is mathematically also using the actual definition of the limits, actual definition of the differentiation, we are able to see that it is not differentiable. Okay, we don't have that differentiability, we don't get any value, it is undefined.
Well, why is it infinity there? Sorry.
Yeah, you are plugging in, right? We have this limit x approaches 0, This is what we have, x power 2 by 3. So we plug this one, x approaches 0. We plug 0 here. It is going to be 0, right? This is going to be 0. So 1 over 0 is infinite, right? This is 1 by 0. It's undefined. Right? So that is why we get undefined there. It's infinite. You can conclude that the tangent line is vertical at x equal to 0. So f is not differentiable at x equal to 0. Okay, let's move next. Okay, now questions. If you are given that f is differentiable at x equal to 2, then explain why each statement is true. Okay, can you try this?
Am I supposed to okay, I can just type it.
Yeah,